So hello everyone, my name is Omar. I'm the practice lead for AI and machine learning at the patterns team at Esri. And I'm pleased to present today with my colleagues, Daniel Wilson, Dmitry Kodinov, and Orhan Aydin, this very interesting topic that we are all very passionate about, AI meeting GIS or machine learning meeting GIS. So I have a quick question at the beginning. How many of you guys have tried to build machine learning stuff or deep learning okay, interesting. And how many of you guys have seen the accidents prediction demo before? Okay, awesome. So I'll gonna have a very quick intro about AI, machine learning, and deep learning, just to have this kind of common ground, on the top of which we're gonna base our talk today. We are going to show 3 demos using machine learning and deep learning with ArcGIS. And the first one is about predicting expected time of arrival of vehicles. It's a very interesting application for lots of industries. The second one, we're going to highlight some demos using existing machine learning in ArcGIS today. And the third one, we're going to dig deeper in the accidents prediction demo, showing you guys the specifics, how did we went through it in terms of the code and the architecture and the parameters of the model. So I want to quickly start with this. So you can see AI across your Facebook timelines and Instagrams and Twitter. It's happening, right? So this is AlphaGo DeepMind beating the top contender using reinforcement learning, which is a kind of deep learning. And the Go game is a 19 by 19 board. It's extremely impossible. It's extremely hard to attack this from brute force kind of methodology because the total board configuration are more than the number of atoms. It's used in Tesla cars to avoid car crashes. As you can see, this car actually has stopped before hitting the point where those 2 cars crashed using different techniques of computer vision and deep learning. It was used to beat this guy, Dendi. Any of you guys play Dota 2? Okay, here's one. So I think you're following up with this. It was developed by OpenAI, which is an institute funded by Elon Musk. Using some techniques, it was able to beat some of the world top contenders in this game. And it's heavily used in cancer diagnosis. It's indeed exceeding the performance of some physicians in early diagnosis of cancer using deep learning computer vision algorithms. So I think I just want to say that it's reality right now. It's no more theory. And this is basically happening for 3 main things. First, computation performance. So right now we have amazing computation performance. We have GPUs enabling us to train those algorithms. So deep neural networks, for example, required massive computation that wasn't really available easily before. The second thing is the data sets. So we have amazing data sets right now coming from telecom operators, social media, sensors. We're talking about at least 30 billion sensors or 20 billion sensors by 2020. And the third thing are the new algorithms. So machine learning and AI are not new. They are there actually since the 40s or the 50s. But there are some new algorithms that you're going to see today, like deep neural networks or convolutional neural networks or recurrent neural networks. AI is the idea of getting computers to be as smart as humans. It has different multiple categories. Machine learning is one category of those. It's about learning from data to derive rules instead of being explicitly programmed. And it has different kinds. So one is supervised learning that we're going to see lots of examples today about, which is trying to learn the relationship between inputs and outputs. So if you want to predict the shape of the object or whether this object is orange or apple, we give it lots of data and different features like the weight of these objects, the texture of these objects, and its label. So it gets trained on this kind of inputs, features, and labels. And whenever you show it new data, like 140 gram of Mumpy, it will predict that it's orange, not apple. We have unsupervised learning that deals with clustering and reinforcement learning, which is another type of machine learning. And deep learning is a subfield of machine learning. It's using a very specific technique called deep neural networks. And it's really good with high-dimensional data like voice, images, text. And it can work with other kinds of data as well. And it's generally good, achieving higher accuracy, modeling more complex problems, automatically extracting those features, so it doesn't really need a human to identify those features in many cases, like images, for example. Like if you want to classify this dog or detect cats and dogs, you don't need to manually mention the features like, hey, these are ears, eyes, mouth, etc. It can automatically identify that these are features. You just need to give it the label and tons of data, and it will learn. So I just want to highlight that fact that AI is a big field. It's existing since the 40s or the 50s. Machine learning is a subfield. Deep learning is a specific machine learning technique. And I wanted to highlight this idea of training very quickly because we're going to use it a lot today. So to have an algorithm that is able to predict or classify, you need to train it. And training means that it needs to learn from data. It needs to have some examples, right? So give the machine some examples, a lot of examples indeed. It will be able to predict the event you're trying to do or classify objects. Like in that case, we want to predict churn, which is the idea of having a customer leaving Verizon, for example, and going to AT&T. This is called churn. And if we gave the machine historical data about all of the customers of Verizon in the last 2 or 3 years, and their features, like the number of call drops, the number of complaints, the subscribe package, the call rate decline for every customer, and the label in that case is whether that customer churned or not. It's going to learn those input-output relationships. And this is called a training data set. These are called features, and these are called outputs. And what happens is that we start training using different models. So we have different machine learning models like regression, classification, support vector machines, decision trees, gradient boosting. We have neural networks. We have deep learning. And finally, we end up with trained model or an ensemble of trained models. And those models actually, whenever they see new data, like, hey, we have a new customer, and these are the values of these features. Please predict for me the probability if this customer leaving the company or not, then it's going to give you a probability. So it can give you a probability, it can give you a number, like the number of crimes per area, or it can give you other kind of outputs with images, for example. So this is quickly the idea of training, and you can think that it could be used in different contexts. You can predict water leakages, for example, if you have the features of pipe age, depth, temperature, pressure, and you have the labels, which are the break at this point. You can predict accents. We're going to highlight this in more details today in a similar manner. You can predict retail sales. You can predict ISIS locations, you name it. But you need to have a labeled data set in order to do this. And we have machine learning in ArcGIS today. We have different functional tools. Oren is going to go through this. That these tools help you doing predictions, do clustering, or do line classification. And these are different tools that we have. I really invite you to play with these tools, try to obtain some work if you are not aware of them yet. In fact, I've personally met lots of people who are not aware of many of these tools. And it's really important to start with what we have today before jumping to customization or integration, right? And we can integrate with machine learning and deep learning frameworks as well, like TensorFlow, Scikit-learn, Azure Machine Learning, you name it. This integration could be happening using the Python API or the R bridge. And I want to start with an example for this kind of integration, where we are using TensorFlow to train a deep neural network to predict accurately the arrival times of vehicles. So with that, I leave it to Dimitri.
Thank you very much, Umar. Let's switch to my screen. It's a little bit more boring than the one of Omar. But before we get to the numbers, let me tell you a little bit more about the tasks that we are trying to address here. This is a research project which we were doing inside network analyst team. How many of you are familiar with the network analyst extension? All right, good. So the network analyst extension is the one which can build routes for you, the one which can assign stops to multiple vehicles in an optimal way, the one which can find best locations for your warehouses to serve, for example, multiple vehicles and multiple destinations, and so on and so forth. There are 6 big umbrella algorithms there and over 20 sub-algorithms inside. So essentially, this is an extension which aim is to solve transportation tasks on a transportation graph for transportation logistics. The deterministic algorithms like routing, vehicle routing problem, origin-destination cost matrix, location allocation, and so on and so forth, they have computational complexity which is proportional to the size of the transportation graph. And for large-scale problems, this becomes a challenge. Because if, for example, we are trying to assign 1,000 stops to 100 vehicles, solving a vehicle routing problem, then the first stage we need to perform as part of that algorithm is to calculate the origin-destination cost matrix between all the stops. So if you have 1,000 stops, then you get 1 million pairs, which you need to calculate. This essentially the ETAs. how long will it take to travel in that particular travel mode under that particular conditions from each of those stops to each another stop. If you have a larger size fleet and larger size operation, like for example 15,000 stops for a day, some companies deal with this as well, with this kind of tasks. 15,000 by 15,000, like it's 225 million ETAs. This becomes very expensive, and it becomes exponentially expensive to solve on the larger geographical areas, because the size of the graph which you need to traverse is growing quadratically, if you are talking about 2D graph. So we try to see what we can do actually to optimize this complexity, and if we can actually approach this complexity problem from a different direction, from the neural network standpoint. The neural network is hard to train, but very easy to use it to infer. Actually, the inference time from it is constant. It's of 1 once you have it trained. Of course, it doesn't give you the exact solution, but many of transportation algorithms can tolerate the non-exact solutions or non-exact costs when you are traversing a graph. So we took a bunch of simulated GPS points. We pre-processed them into so-called journeys, which look like this. Essentially, a bunch of CSV records which have 5 input columns, which is x1, y1, x2, y2, essentially your origin location and your destination. So where you're traveling and where you're traveling from and where you're traveling to, and the departure time. And then the ground truth column was the actual cost. How long did it take to travel from A to B at that particular moment in time? So just 6 column totals in total. So x1, y1, x2, y2, start time, and the ground truth data against which the neural network was trained, actually. And we were training it with TensorFlow, with Keras wrapper on top, using GPU. And we had about 300 million records like this for the area of California and Nevada, which is about like 35 million junctions on transportation graph. Fairly large and representative area. And it took us actually almost 8 months, actually more than 8 months of constant running experiments, tweaking hyperparameters, looking for different distributions of spatial and statistical data in the training set, looking for different model architectures. And surprisingly, one of the simplest model architectures, actually, the one which worked is an MLP, a multi-layer perceptron. How many of you guys know what MLP is? Okay, so a multi-layer perceptron is essentially a dense network, a dense neural network with layer by layer neurons connected one layer to another, each with each. And you have trainable parameters, essentially, which are being adjusted during training to adjust that flow of the input values to come to the output. So it looks close to the ground truth data. And since our ground truth data is in minutes, the output of the network is also in minutes. So the end product is taking essentially 5 numbers in, so 2 stops and departure time, and it outputs just a single number. It's travel time in minutes. It's interesting also that although this is what you can see here on the screen, this is the only training data it was trained on. The neural network during training was able to pick up the notion of not just transportation graph and how it looks and what does it mean to travel on it, but also how the travel times on this graph change depending on the congestion, on the road congestion. And this is a quite interesting effect, which I will show you later in the end of the demo. But this is something interesting and indicative of very big potential of machine learning as a tool to pick up some not very obvious and hidden dependencies inside the training data. Okay, so a little bit more about the architecture of the neural network itself. One of the most successful options, as I mentioned, is a multi-layer perceptron here. Although we are still continuing the research and we are looking into the 1D convolutions at this point and see maybe we can actually do even better there with a convolutional neural network. But the MLP was producing fairly good results. And the architecture of that MLP to cover the California and Nevada geography had 16 hidden layers with about 10 million trainable parameters only. And we were training it on as a regressor, essentially minimizing the mean squared error. But what does it mean, essentially, to get 14.9 mean squared error at the training epoch? It's not that obvious. So the question was how are we going to verify that our neural network is actually learning something useful? Does it even work? So we ended up first taking a set of routes which were not seen by the neural network during the training and asked it to actually predict the training times for the routes which were not present in the training set and compare it against the ground truth data, which the neural network didn't see, of course. So this chart here which you are looking at is like a bucketed per minute standard deviations of how the prediction produced by the neural network varies from the ground truth data, depending on the route length. So we can see that for the short routes from 0 to 25 minutes, the standard deviation grows here in a fairly linear manner. Then we have a fairly constant plateau from about 30 to 40 maybe minutes to about 2 hours. And then we get a spike of uncertainty. Well, this chart actually gives us a way better insight in how accurate and on what particular routes our trained neural network is. And actually, this is a nice tool because it also allows me to compare different models at different stages of their lifetime or the training time. Like for example, here I'm looking at the standard deviation chart of 3 different models. And I can choose which one works best. So this is a nice training, a nice tool to verify the training quality. But we can take it even further down the road. Besides just a constant of 1 time on inference, the throughput when run on GPU on inference of this neural network is tremendous. So if using deterministic algorithms, you can calculate about like 100, maybe 150 ETAs from 8-core machine per second. With a neural network and powerful enough GPU, you can actually get 3 orders of magnitude more per second. So it's a tremendous throughput. But it outputs just one number, right, for a given set of stops. So what can we do to make it a little bit more visually inspectable, if I can say this? Well, what we did essentially, we wrapped this neural network into a WMS endpoint, which essentially outputs a raster. And given the extent of my map here and the Python API, it takes the central pixel of this map and takes all the other pixels of this extent as well and calculates the origin-destination pairs for the given time. So essentially, this is about like a 1 megapixel picture here. So about 1 million ETAs are calculated to form this blue blob here. And this is actually an isochron. Isochron with cutoff of 20 minutes in travel time. This is actually like a 3D surface because we have X, Y, and T which is a result of projection of that multidimensional function, which is represented by the multi-layer perceptron. And this represents the time it took to travel from that central location to every other pixel of the map. And the value of this pixel is time in minutes. How long does it take to travel in minutes? This is interesting. So for those of you who are familiar with network analyst and surface area polygons, in particular surface area solver, this might look familiar because surface area polygons, they represent the time it takes to travel from the origin or from the facility to outside on the transportation graph at a particular given time. Well, let's, using Python API, let's overlay one on top of another and see actually if it's going to work. Let me run a couple pieces of code here, and now I'm going to place one on top of another, and here you go. So we have the blue isochron, which is represented by the neural network, and the red one is a surface area polygon, which was calculated by the deterministic graph traversal algorithm, which was running on the actual ground truth data, on the actual transportation graph. And as you can see, they match very closely. And this is a quite impressive result, and which I think validates that MSE value and that previous chart which we have seen before. At the beginning of the presentation, I said that based on that input data, which is just 5 columns, the neural network was able to pick up the traffic congestion patterns. And now I'm going to show you a video, actually, showing how for one single location in San Francisco, we just built that isochron, which I just showed you, and we colored it a little bit differently, but we asked it to render that isochron for a different departure time from the downtown San Francisco. And now you will be able to see how, from the perception of that neural network, the traffic in San Francisco changes throughout the entire week. So let's see. So this is 25 minutes isochron and 7 days worth of time here. As you can see, it's getting the most expansion during the night time, during the night hours, and most contracted during the business hours, and beginning and the end of the business day. As a little bit more technical thing, I don't know, do I still have time?
We have like 2 minutes.
Okay, 2 minutes. Okay, good. For the enthusiasts of deep learning and the neural networks, I can show you another visualization in the last 2 minutes, which shows how the level of entropy of the neural network drops during the training. So the neural network starts with complete noise, and then during the training it gains some understanding of that underlying training data, and starts producing more and more meaningful and close to actual desired results. And this is again another video which starts with again the same area in San Francisco. It doesn't have base map, but this is the same area in San Francisco. And as you can see, the predictions are quite round, which means that they are not that good at this point. But as training progresses, this blob shape becomes more and more detailed, because it starts gaining the understanding of underlying transportation network and the patterns inside it. So, and at the very last stage where I just showed you that results of that neural network, it has this particular shape. So this is the shape which you have seen in the previous demos.
I think this is scary in some aspects, right? I mean,
all right. I'm done with my part. Thank you.
Thank you, Dimitri, so much. That was an amazing demo. And for me, actually, I see lots of applications for this, right? So we can use network analysts today to ask questions for now, taking real-time traffic data into consideration, real-time weather data. But if we want to predict for some point in the future, And we want to take the seasonality of the data into consideration, like the different weather, the different times of the day, the different kind of vehicles, the different type of products. This would be extremely helpful, right? Because to learn the difference with this kind of seasonality, the variance according to those parameters, we need to learn this, right? And machine learning is definitely a way of doing this, right? Thank you, Dimitri, so much. So for now, we are going to shift gears to the accidents prediction demo to go through the technical details. How was it made? We had a quick kind of view of it in the keynote and in the EPC. We demonstrated how we have used Azure Machine Learning before. Now, today, we're going to demonstrate how we have used Python Scikit-learn XGBoost to do this. And after that, we will show you some examples of demos using existing machine learning in ArcGIS today.
All right, let's just jump right into this. So about half of you have seen the demo of this on a previous day or session, right? So our goal here is not to predict, exactly where along these roads where these accidents are going to happen, but try to estimate the risk for certain regions, certain areas in the road that are higher than normal. So the first part of this whole process of training a machine learning model is determining what are we actually going to use to make these decisions. Supervised machine learning requires some sort of input in order to actually make these determinations. So for the network stuff, we use the origins and destinations. In this case, we're going to use a lot of features related to possible causes of accidents. In this case, we're looking at weather, such as wind speed, temperature, whether it's icy or snowy. The day of the week has a pretty dramatic factor on how many accidents we expect to see in a day. The time of day, you might expect to see more accidents at rush hour, either around sunrise or sunset. The month of the year, partly through weather, but partly due to different travel patterns. More people might take vacations in the summer, so you might see different factors there. And the list goes on. There's tens of variables, potentially more that we can include in this model to try to estimate the probability of accidents. We're using, I think, pretty much we're using everything on that list. And then there's a couple extra factors that we're adding that are less interesting, but to help the model actually perform a little bit better. We have a 7-year history of accidents, and that's what we're using to actually train this model. I think there's roughly 400,000 accidents, roughly 500,000 road segments. And if you think about this, trying to analyze all these factors, you can start to do this analysis by hand, but to actually perform this at this kind of scale becomes exceptionally challenging, and that's where machine learning comes along. We can use machine learning to train this model and try to identify what these important factors are, and then run this for future predictions. So I'm going to get out of PowerPoints because no one likes PowerPoints. Okay, so we're at the guts of everything here. Okay, so let me actually start out in ArcGIS Pro. That's where this whole process started. There's a whole bunch of spatial data sets that are available through the portal that were used in this analysis. So for example, the actual road networks were brought together with other data sources. We first pulled the road network, so we had our most complete data set to represent where the accidents were occurring. We brought in the annual average daily traffic as a way to estimate the general traffic volume that we see on particular road stretches. Signalized and unsignalized intersections, I think about 27 weather stations across Utah. There's actually more weather stations, but these are part of a global hourly weather feed that NOAA sends out, so we have an easy way to obtain the data quickly. Part of what we can do in Pro is actually explore some of these relationships. So if I zoom in on these intersections, you can readily see that a lot of these accidents are happening in close proximity to intersections. I think that's a very important feature. We want to make sure that some of these major intersections where these accidents are happening can be identified by this model. Road curvature, so how curvy a road is, we think is an important factor in accidents prediction. We especially think that matters when you compare it to weather. So you can imagine you have an icy road that's a little bit curvy. Someone's driving down the road a little bit too fast, and they aren't able to keep in a straight line. So that's another factor we're adding. And then driver distractions. So there's a lot of possible features we could add to try to model the driver distractions and causing accidents. We just use billboards for this case, but there's a lot of different things we could add in to try to determine distracted driving causes. So once we have the data, that did not work at all. There we go. Once we have the data, we've kind of gotten a feel for what we want to use. We actually used ArcGIS to actually process all of this data. So we created a file database, created some paths to remote files, and we had the CSV file of all of this. Using ArcGIS, and there's a lot of miscellaneous geoprocessing, calculating the road curvature. We used sinuosity as a way to measure the curvature of a road. That's just the ratio between the length of the road and the distance between the endpoints. So if a road's really curvy, you expect it to have a higher sinuosity. So there's a whole bunch of calculations here, joining up the weather data, calculating which stations are near to which roads, and then actually assigning the data. For the purposes of this demo, we used 50 feet as our cutoff. That is how we prepare the spatial data, but after we did that, we used the ArcGIS Python API to read all the data into a spatial data frame. It's a very convenient way to actually do the training data preparation using pandas for the rest of this. So we did a little bit of feature augmentation. We just did some basic joins of the roads and the feature data. And then finally, we ended up selecting which features we actually want to use in this model, and there's that list in this case. So we're using the road direction, the street type, the surface type, the annual average daily traffic, and so on that you saw on that slide. Finally, we can actually get to the point where we train the model. I'm loading that CSV file. So right here is just a list of all of those features together. What we've done in this case is we're modeling this as a classification problem. So we're just trying to say, for this given road segment in an hour, what's the probability that we're going to see at least one accident on that road segment? We're not trying to model the number of accidents, but we're trying to model for a road segment what the expected number of accidents is. So what we do is we assign a target of either 1 for, yes, there was an accident, or 0 for, there was no accident. And that's what we're actually going to use to train the model. So we've actually investigated several models, including deep neural networks and other ones. The one that we found works most consistently for this type of problem and has a pretty fast training is actually gradient boosting. There's a library called XGBoost that's available through Conda and other places it's really high performance. In this case, we actually have modified some of the initial parameters here, but we can train this tree with a max depth of 10. We tried different ranges. 10 seemed to be the point where we had the best performance. And then there's other parameters. For the most part, we use the defaults. There's a lot of parameter tuning you can do through cross-validation, grid search. And we found that the default parameters honestly worked best for this type of problem. One of the advantages of gradient boosting is you can get a feature importance score. So once you train the model, you have a graph of which features were important in making these determinations. And you can see on our graph, the model determined that temperature was the most important variable. We've actually gotten a few questions since we did this initial demo about, hey, why is temperature the important factor? Temperature doesn't make me crash my car. And temperature is really more of a proxy for other variables, including the time of day, where the sun is, how icy the roads could potentially be. So maybe the roads are wet, but we don't have records of where roads are always wet. We have the data we have, and temperature is a consistent way to actually act as a proxy to some of these other important variables. And of course, we expect to see accidents where we've seen them happen in the past. So that's our way of modeling the factors in the roads that we couldn't extract directly. So using that historical data, we're using that to predict the future. The road orientations, that would determine if you're driving east-west, into sunrise or sunset, you might see get the sun in your eyes and get into an accident. So actually, I didn't show this at previous ones because I just generated this plot because I wanted to see for myself, when you look over time, how good is our model? So I'm going to show you spatially how it looks, but I'm going to show you another view of the data here, and that's actually showing a time series of how many accidents we're predicting versus how many actually happened. In this case, the orange line, can you guys see that okay? Let me zoom in a little bit. Maybe. Try. There we go. Okay, so the blue line is the actual accident counts. So for the month of January 2013, which is the month that had the most accidents in our data set, you can see that our predictions, the orange line, actually matches up pretty well in a lot of cases. It's not perfect, and we don't expect it to be. This is a probabilistic model. But for the most part, when we're predicting, we're saying that there's going to be some number of accidents, it actually holds pretty consistent. Okay, so now I'm going to show you a few map scenes of this. So this is an area a little bit north of Salt Lake City. For each road segment for this hour, this is December 3rd at 3 p.m., so right before rush hour. It's rainy and icy. This is a map of our predictions. So green is low risk, yellow is kind of a medium risk, and then red is high risk. And then if we overlay the actual accidents that occurred on that day, for the most part, we're getting them. Pretty much every accident on here, we are correctly, it's occurring on the segments that we're predicting as high risk. For example, you go over to, oops, a little bit touchy today. There you go. So you go over to this one. It's this little road segment surrounded by kind of a bunch of green roads, but for whatever reason, this particular road has a higher risk of accident, and in this case had an accident. This is south of the main downtown Salt Lake City. So you can see there's a lot of highways here. I think this is Interstate 15 going up the center here. If we overlay the accidents, again, you can see we're predicting them for the most part on areas that have a high probability as estimated by the model. Same thing here. I think we're overall doing pretty well. And finally, one more. This is an area where, for the most part, there weren't that many roads that were predicted as higher probability, but you can definitely see that those highways are higher than normal, as well as this entrance to a highway right here, this on-ramp. All right, that's all I have for you today.
Thanks, Daniel. That was awesome. Thank you so much for this. And I want to quickly elaborate on that. 3 main points. The first point is the crucial role of ArcGIS in doing that. We needed to use ArcGIS Pro or ArcPy heavily, lots of geoprocessing functions to come up with the training set. The spatial features like proximity to intersections, the road direction, the sun direction, you name it, we have used different geoprocessing function for that. And to overlay the weather and join the weather with every segment, we did spatial joins and proximity analysis. And then we are considering to model weather using some interpolation techniques. So that was one part. And then we pass the training data to the machine learning engine. And once we are predicting, we are taking this to another level to act upon it. So we are envisioning scenarios where we are using location allocation services to dynamically allocate ambulance cars, for example, to reach faster to those top areas of high risk, right? And we are continuously working on our model to fine-tune it. We believe there is room for improvement. We are trying out new features. We are experimenting with deep learning kind of techniques as well. So this is an ongoing kind of work. So maybe when you see this kind of applications, you think that, hey, okay, this amazing world of machine learning and deep learning is happening outside ArcGIS, and we can integrate with it. But do you know that we have existing tools today that are machine learning tools already in the software that you can use it to do amazing stuff? That's what I want to show to you right now. So my colleague Oren will walk us through the existing tools in ArcGIS that you can start using today. You don't really need to have a PhD or a deep learning background. You just can use them. Oren.
Thank you, Omar. So I'm going to start with a fundamental. Oh, I am 3. There we are. So I'm going to start with a fundamental question that you have after Omar's intro. Why should you use machine learning in ArcGIS? Because there are libraries out there. They are pretty well established, so what is the difference? So in this first demo, I'm basically going to talk about some machine learning methods that exist in a well-known library, which is scikit-learn in Python. I'm going to integrate some functionality. I'm going to try to solve a problem using mainstream machine learning methods. And then I'm going to compare the results to a machine learning method we have in ArcGIS that is purely spatial. So the difference between the two will be the first portion is going to be a mainstream machine learning method applied to spatial data compared against a spatial machine learning method applied to spatial data. And we're going to look at the differences. So the first example I'm going to show you is a regression problem. So I would like to establish a relationship of a quantity that I'm interested in. So this example is from weather prediction. I want to understand the weather. And in the United States, I have hard data where I measure weather daily at a very fine resolution. And what you see on the screen here are these station locations that capture temperature measurements constantly. A lot of them are close to airports, and this is actually a very small subset of this data set. So if I want to predict weather, I cannot use the station data because I need to predict it into the future. But what I can do is I can take a model, and I can form a relationship between that model and my measurements. And after I calibrate that model, I can use it to forecast what's going to happen. And this general idea applies to crime. It can apply to sales. It can apply to anything that you want to forecast into the future. So the elements of this problem is first the station data. So what do they look like? It's basically at a given time, it's a measurement of temperature, a maximum, minimum, and an average. But unlike many of the data sets, similar to many of the data sets, there are some bad eggs in this basket. There are missing values. So this is going to be the first challenge. How do you deal with that? And the second challenge is, as I said, these are the stations where I have actual measurements. And there is a model, which is called a global climate model, where scientists simulate parameters pertaining to the climate. Not all of them are direct temperature parameters, but they're somehow related to temperature, such as wind speeds, wind directions, humidity at different levels, pressures, and so on and so forth. And all these parameters are simulated at a coarser grid like that. And the second challenge is, how can I take this data that is simulated on these red points, estimate it at where the stations are, so that I can form a regression at those locations, right? So that is the second challenge. So one of the beauties of working in ArcGIS platform is I can just define a very simple model. So what I'm going to do here is I'm going to take my station data, which, as I said, had some missing values in it, and I'm going to use a tool. And this is not even a machine learning tool, but this is a utility tool we have in ArcGIS Pro called Fill Missing Values. And wherever I have missing values, I'm going to fill it using the average of my 6 nearest neighbors. And then I'm going to have a complete data set. It's not going to have these -999s anymore. But this new data set is actually going to have values everywhere filled in. So this was my first problem. I've completed my data. And going into any machine learning practice, this is a big challenge. How do you clean up your data? And if you want to clean up your data in a spatial way, you have a tool to do that in Pro. Now the second challenge. How do you estimate the values on this fine grid where these red points are, where the station locations are? Well, you can create an interpolation surface, again, which we have a tool for, called empirical Bayesian kriging. This is a kriging system that estimates an optimal interpolator for this model parameters. And one of the advantages of empirical Bayesian kriging is it doesn't have one of the limitations that simple kriging or ordinary kriging or these methods have, that actually it can capture non-stationarity in your data. So if you have patterns in your data that are constantly changing, this method can adapt to that. So first, I fill all my missing values, and then I estimate my model parameters at my station locations. So at the end of the day, I have one data set that I can work with. So just to show you the outputs of the EBK regression, it basically takes the models that are simulated at these locations, and then it creates a continuous surface for every parameter. This global climate model has 19 predictors. I'm only going to show you 2. So this is what the sea level pressure looks like. And this is the airflow parameter. I think it's just taking a time to draw it. It's a little blurry. But then, after I have this continuous surface, I can just extract the values at these locations, which is very simple. So we haven't even started the machine learning part yet, but we already cleaned up our data and brought it to a form where we can actually do some analysis on it. So just to introduce you to the problem, in this problem, I have 19 predictors. For the climate example, I have 19 indirect predictors of climate. If you're interested in retail, you might have different indicators that you want to tie to a target variable. In my case, this target variable is the local average temperature. So I want to form a relationship between these predictors and something that I'm actually interested in. As I said, to do that, I'm going to compare 2 mainstream machine learning methods. First of them is a support vector machine, which is widely used from the sklearn library of Python. And the second one is ridge regression, again from the scikit-learn library. And I'm going to compare it to another regression method called geographically weighted regression in ArcGIS Pro that is a purely spatial regression model, and just look at the results. So one way I can go, and some of you might really like that way, is I can just write code to do it, which I did. But instead of just calling scikit-learn on its own, what I did here is I wrapped it in what we call a PYT. This is a Python toolbox. So if you're asking what this does, if you haven't used this before, I can actually take scikit-learn functionality that is defined in these libraries from linear model libraries and wrap it. I don't have time to go through the details, but I'll be sharing this code with you so you can actually just download this. And if you have scikit-learn library, you can consume functionality directly into Pro. One thing I can do here is I can take the support vector machine library and make it look like a function in ArcGIS Pro. So this doesn't exist in ArcGIS Pro in its current form, but that little code snippet I showed you wraps that functionality around and allows me to use it in ArcGIS Pro. The advantage of this is, since this is a spatial problem and you want to see the map of your result, you can keep on tweaking your values and then see the effect on the screen. So as I said, in my system, I have 19 predictors from the global climate model, and all 19 of them are there. And using those, I want to predict the monthly average temperature. So another thing I want to show you, which is the advantage of an approach like this, is I'm going to have some diagnostics that I want to run. For example, for the support vector machine, I want to see what my error is like. And I want to see how good of a fit I have. So I have a custom plot that is going to pop up on the fly. This is all hard-coded into my PYT. So let's run this. So this is a Python plot that just pops up when I run this PYT. So what you see here is, after I do my fit and predict, the red lines are the temperature measurements observed at stations. And the blue line that you can barely see is the model fit. You can only see a small mismatch here. So on paper, it looks like an amazing fit. It looks like I have a great model. But I know that this is a spatial problem. So is it actually a good model? So the second thing I'm going to check is the map. How does a temperature map over the United States look like? Well, it doesn't look that well. When we look at the temperatures ranging from 5 Celsius to 22, what this basically tells me is there are some portions of US where one town is in winter, but right next to it is in peak summer. That makes no sense. So what happened here? So this global machine learning method, the way I trained it and the way I applied it, it overfit to my data. It did a very good job at predicting temperatures here, where the stations are. But the minute you moved away from a station, it couldn't predict anymore. It trained too much on the data, and it couldn't generalize it. So I'm going to use another method called ridge regression that overcomes that by penalizing fitting complex functions to your data. So it is a good balance between having a good fit, but using a complex model to do it. So the main idea between ridge regression is how good of a fit can you get using a simple model? Again, this is from the scikit-learn library. Again, this is not a spatial method. But using a PYT, I can directly consume it. Again, I have my 19 predictors, and it lives in the same PYT. I'm going to predict the monthly average temperature. So one of the parameters it has is the regularization strength, also known as an alpha parameter. So what this basically tells you is how much do you want to penalize for fitting a complex function to get a good fit. So as a user, I don't know that. But the good thing is there's a functionality I can use in scikit-learn that can do that for me. And I integrate that into my code, where I'm saying that if a parameter is not put in by the user, call the scikit-learn function that can automatically detect it. And it's exactly going to do that. And it's going to show me some diagnostic plots again. So I'm wrapping this Python functionality in this tool so that I can do machine learning to solve my problem. So let's run this ridge regression. Again, the parameter I didn't know, it basically showed me the optimal parameter, the parameter that gives me the lowest error. And here I can also throw a message. It's going to say that it's going to use this number. And I'm going to close it. And this shows the match. So this looks like a much worse match than before. You can actually see the two lines this time. But I think you're kind of getting the trick here that this is a spatial problem. A result that looks bad on 1D, let's see how it looks on a map. So this is the ridge regression result, which looks like a much plausible result. You can see the patterns in temperature that you would expect. You see that gradual change from south to north. You can see the impact of landscape and the mountains in different parts of the US. So this may not be the model, but that's a much bigger improvement over the support vector machine. So one thing I want you to keep in mind is to get this map, I use 19 predictors. So now let's work with a spatial method, that is geographically weighted regression. For that, you don't need a PYT because we already wrote that for you. It comes with Pro. It's a functionality that we developed within our company. So this time, I'm going to use only 3 variables. I'm not going to use 19. I'm going to predict temperature using only 3. But this integrates the space in an inherent way to the algorithm. What it does is it basically forms a linear regression model, but it weighs everything with respect to their proximity. For example, if I want to form a relationship between the predictors, the 19 predictors, or these 3 predictors and the average temperature for this point here, it's going to weigh the data coming from closer points more. And as you get far away from this point, like these ones, it's going to weigh them less and less and less. So the further you are, the less related you are to this point. And this algorithm automatically handles that by subsetting and then forming ordinary linear regression at these spatial subsets. So I used 3 predictors, and I predicted the temperature, the average temperature. So when I look at it, the result, this actually looks like a very close result to what I get with ridge regression. This looks, actually, it resembles the patterns I see here. They are more smoothed, yes. But I was able to dump 16 parameters that I didn't need. I really honed into parameters that really mattered. One of the requirements of this method is these input parameters or these predictors need to be independent. So you have to do some analysis to pick the right ones. But after you do, you can actually create a method that has exponential power very easily. So this is one of the tools we have for regression. I will quickly show you our clustering suite. So this is the data set I'm going to show you really quickly. For those of you who used Waze in the past or still are using it, so this is a Waze data set. Waze was an alternative to Google Maps. It got bought by Google Maps. So it's basically a navigation algorithm, a navigation program that you can use to get from A to B, just like Google. And a functionality that it had over Google Maps was you can actually draw pins. Hey, at this point there's a slowdown, at this point there's an accident, at this point there's a police officer, so on and so forth. And this data set is coming from Waze, and these are the locations that people reported slowdowns on their phones. in LA traffic, and this is during 5 p.m. peak hour on a Friday. So this might be the traffic that you encounter if you're flying out of LAX today. So I want to find some patterns. I want to find some spatial clusters here. So what does a cluster mean? I'm going to be addressing this using density-based clustering methods. What density-based clustering implies is, given this dense data set, points all around the roads of LA, which ones are denser than others? Which are these dense hotspots of traffic? What it means for traffic is, if at a small distance, there are many people saying that there's a slowdown, that means that it's a legitimate slowdown. So I'm going to use one of the machine learning methods we have, which is HDB scan. And you can choose different ones. So on this data set, it can detect these clusters. So when you look on the map, this actually makes a lot of sense. You have a big cluster in downtown LA, the blue one. And you have patches of traffic going outside of LA. And these are a lot of people that are commuting in and out. So these are people going back home after 5 p.m. So you have these small flanks of traffic. And you have places where there isn't considerable traffic because there aren't that many exits, or the exits are in such a way that it doesn't really create a congestion to people. Or there is a fast track lane and the traffic just moves smoothly. So by using a method like that is inherently spatial, you can make sense of a dense point data, and you can extract clusters that will allow you to infer spatial intelligence from your data. These were the tools that I wanted to show today. And we are adding more and more machine learning functionality that you'll be able to use very soon.
Thank you. So, yeah, we have this today in ArcGIS. I really invite you to play with the different clustering and prediction algorithms. And we're going to share some of our integrations as well publicly so that you can play with them. So yeah, that was it for today. And anyone has any question? Any questions? Have a question?
You said time costs change by time. When you do your modeling, so I don't know if you take in consideration the time change during, in a peak hour, in a morning, and how to apply the result in a time cost in the network itself. So when I'm using a network analysis, I should get that result also in a network.
Yes, so the question, as far as I understand, is whether the traffic congestion is being used in the training data or is present in the training data. Yes, the answer is yes. If you build, or if you find, for example, a route represented in the training data by the same origin and destination stops, but different departure time, the cost will be different. And this is how the neural network actually gets the notion of the congestion or the traffic. And this is why you could see that isochron pulsing as different departure time is applied to it. Did I answer your question?
Yeah.
Okay.
With the models that you guys do have, are you guys testing anything related to citations as it relates to crashes? For example, the big focus that you guys said is you're estimating the risk on the road. So officers out there, say, hitting a fishing hole, they could be causing those crashes. Are you guys taking a look as those citations could also be leading into those crashes in certain times?
That's not something we looked at, but that's a really good idea. We should. We're going to try to apply this model in different areas and different, maybe focus more on urban centers, and that would be a great data set to add in.
Okay, thank you.
So, I get her before.
Yeah, I was just wondering, how did you create the non-crash component of your training data set for those crashes?
So I actually jumped over that really quickly.
Oh, sorry.
Let's see if I can get to that. I did not. I should have talked about that. Okay, so we actually wrote this routine. that does negative sampling. So we have 400,000 record of accidents. For each of those, we wanted to get a training set of times where accidents didn't happen, but were fairly similar. So we wanted to have conditions that were similar to when accidents occurred, but an accident didn't occur. So we can focus on those subtle differences and train a better model. So what we did was, for each of the accidents, for the number of samples we wanted to generate, which in this case for the model was 4 times the number of accidents. So that gave us roughly, so right here, 4 times the number of features. That gives us an imbalanced training set, but gives us a lot of weighting on, well, most of the time accidents don't happen. So let's try to figure out what actually differentiates those. So for each accident, we randomly either chose a new road for that accident to occur on, but kept the same hour of the day and the same day of the year and all of that the same. Or we changed the hour, or we changed the day of the year. So that gave us a big sample of accidents that were similar, but we changed basically one feature to make them different.
Did you factor in how much each individual road
We tried weighting based on the number of accidents on the road. So you could sample roads that have higher accidents, which obviously lowers the performance of our model because we're looking at places where accidents are occurring and then saying, well, what are the very, very subtle differences that made an accident occur here versus there? But that can actually strengthen the usefulness of a model like that too.
Regarding the accident predictor, you have a bunch of different factors. Which one is more important than accident? So you have a bunch of number we associate to those factors. So how do you calculate those numbers? Is you using regression model or something else?
To calculate this chart?
Yes.
Yeah, so the value here on this chart, for example, for temperature, it's 579, is the number of times that feature was used to make a decision by the algorithm. So the way the algorithm works is that there's a whole bunch of decision trees. So is the temperature greater or less than 0? Is the accident count greater than or less than 50? It goes through a sequence of those decisions, and the number of times that feature was used in all of the trees is 575 for temperature, and then they're ranked based on how often they were used by the model. So basically, if it's an important factor, you expect it to be used more in the model than other factors.
So this number is came from the model, or?
Yes.
Okay.
Yep.
Okay.
There's other ways of measuring that. So this importance type here is weight, and that's the number of times that it's used. It's actually the sum of the tree weights. There's also gain and cover, which are one of them is related to the gradient, how much the model changes when you change that decision, and then I can't remember what cover is.
Okay, can I ask what's the name of the model?
Yeah, we actually used XGBoost as the library.
Okay.
So it's a gradient boosting library, performs really well. It's really easy to use, high performance.
Yeah, okay. Since actually we are using the very similar approach in our model, which we are using Cox model in our company, but I'm not sure it's any similarity on this kind of two model. So,
which model is it?
Cox. It's a regression model.
Okay.
So we can
okay.
Yeah.
I'm not sure that was not a model we used for this analysis.
Okay. Thank you.
Anyone has any other questions? Okay, thank you so much for coming today, and I invite you again to play with the existing machine learning in ArcGIS, and we're going to share some of these code online. So thank you for attending, and have a great weekend. Thanks.